Hello everyone. In this video I'm going to tell you about free body diagrams. And these are graphical representations, graphical reps of bodies or systems, or parts of bodies or systems, and their interactions with the world around it. Okay, so when you're drawing a free body diagram, there are two steps. So the first step is draw a boundary. And that defines the free body diagram. It defines what's inside and then defines what's outside. And then two is draw representations of interactions of the free body diagram with the rest of the world. So conceptually, you can extract the free body diagram from the world and through its interactions describe what it does when it's actually sitting in with the world. Okay, so let's take a simple example of a box sitting on a box. So here's our simple pictorial representation, 2D projection. I'll call one box M1, we'll call one box M2. Let's say this thing is sitting in the field of gravity. Okay, so the first thing to do if I'm going to draw a free body diagram is choose where I want to draw the boundaries. So for this example, I'm going to choose the first box only. Okay, so that could be one choice. Another choice with these two boxes is I could choose box 1 and box 2, so M1 and M2. So I'll draw the squiggly line to denote that, and so in this case I'll take as my boundaries M1 and M2. So the boundary is on the outside here, not this part here. And on a third example, I'm going to take M1 and part of M2. So remember, we can take part of a body, and in that case then the boundary will be M1 and it'll be part of M2. This will be part of 1. Okay, so I've drawn the boundaries. I've defined what's inside and what's outside. So in this case, the boundary of the box is M1, is around M1, so everything inside is inside the free body diagram, everything else is the outside world. So if I want to draw the interactions with the outside world, I'm going to draw these through forces and moments. So these are the vector quantities that we've talked about. So that's how the free body diagram interacts with the rest of the world. In this case, this box is sitting on a table. I'm going to draw its interaction as a force, which I'll call N1. M2 is sitting on top of it. It interacts with this at the boundary. I'll call this. And it also has a weight. So here's a weight. I'll draw this just on the side and have a weight. And this comes from weight of M1. Okay, so maybe apply to some point here. All right, in the second case here, again, it's sitting on the table. That's a force. In this case, it has a weight. And that comes from M1 and M2. Right? And in the third case, again, it sits on the table. So there's an interaction force here. In this case, part of the box sits on top. And it also has a weight. And this weight is from M1 plus part of M2. So in the free body diagram, we just denote the interaction. Parenthetically, I've just described it in a little more detail. Okay, so let's look more at the interactions. So again, the interactions with the real world are represented on the free body diagram as external force moments. Now I'm going to divide these up into two categories. I'm going to call these body interactions. And these act over the entire volume. So of course our most common example is gravity, which acts on all the particles of the box. And 2, by other categories, would be called surface interactions. And these apply across the boundaries that we've defined. Okay, so e.g. anything in contact with the body. The table, for example, the box on top. All right, let's finish off with an example here. Okay, so let's take Mark. Mark has gone off fishing, so that's why I'm here today and he's not. Mark, of course, is holding his coffee cup, and he's caught a fish. Let's draw the fishing pole. He's got a fish here. Fish is not happy, Mark is happy. Okay, so let's do the first thing is draw the boundary. So let's select as the boundary Mark, and we'll pick the coffee cup as well. So we'll draw the boundary that just encompasses his body. It'll encompass his hand, but not the fishing pole. Okay, so we've defined what's inside, that's everything inside, the body and the cup, and everything that's outside, ground, fishing pole, etc. All right, so let's draw a free body diagram. We have the body, right? There's a contact force that he's interacting with from the ground. Right. There's a body force, his weight. Now, what else is acting on Mark? So his hand, let's draw his hand in here. Let's draw the coffee cup too. His hand. So his hand is inside, the fishing pole is outside. So how does the fishing pole interact with his hand? Assuming that he's holding the fishing pole so that it is level, then to maintain the level position, there needs to be a force. So the pole is pushing down on his hand, so he's pushing back on the pole with an equal and opposite force, Newton's third law. And to keep it from rotating, right, as you can imagine holding out this fish, it's going to rotate. There's going to be a moment applied to his hand and the pole. So here, again, I've drawn the moment as a curved line. It is acting about an axis, which is coming out of the page. And the last thing I want to say is that a very important point here. No internal forces. So don't draw any internal forces or moments on the free body diagram. All right? So for example, Mark is holding the coffee cup. He is applying a force to the cup. The cup is in contact with his hand. It's applying a force to his hand. Those are equal and opposite forces. They cancel out. At the boundary, there are equal and opposite forces, but since the hand is at the boundary, inside the body are the forces from the pole to the body. If I were to draw a free body diagram of the pole, let's draw a free body diagram of the pole, then he's going to have an equal and opposite force here, in a moment here. But in the case of Mark, this is the outside world, so that there are no forces to cancel these out. Right, so this also would have something like the weight of the fish. And perhaps a weight of the rod if you wanted to consider that as well.